Okay, class, let us start the fourth tutorial of the course Symmetry, Stereochemistry and Applications conducted by NPTEL. I hope I'm audible to you all and my slides are visible. So till now we have covered three tutorials on this course whose course instructor is Professor Anshuman Roy Chaudhary from Aizer Mohali. I am Deepika, your PMRF teaching assistant. I'm doing my PhD in chemistry at IIT Bombay. So in this fourth week of video lectures in this course, Sir has covered the topics conversion between Sawhorse-Newman projections as well as Fisher projections of organic molecules. He has also covered absolute configuration of organic molecules like RS nomenclature, specifically allenes and biphenyls, where there are no chiral centers present. Still, they contain optical activity because of the presence of chiral axis of symmetry. So, such etrop isomerism was also covered. Let us start today's tutorial where we are going to solve a few questions on the topics covered in the 4th week lectures. Before moving to the questions, let us go through these easy examples so that we can brush up the concepts which are revolving around RS nomenclature. So in the first example given here, you can see we have 4 substituents present on the carbon center here, which are one hydrogen, one methyl group, one amino functionality, as well as a carboxylic acid. So priority wise, as we all know, when it comes to RS nomenclature, the first priority is given to the substituent where the atom linked to the chiral center has the highest atomic number. So among all these 4, nitrogen is having the highest atomic number. So this will be given the first priority. After that, we have 2 substituents where carbon atom is linked to the chiral center. So when it comes to methyl versus carboxylic group, as we know that in both the substituents, carbon atom is linked to the chiral center. Then we have to look at the next atom which is linked to this carbon atom which is linked to the chiral center. So here in methyl, hydrogen comes after the carbon atom. But in carboxylic group, oxygen comes after the carbon atom. And as we know, oxygen is having the higher atomic number. So the second priority goes to the carboxylic acid group. And hence the third priority will be given to the methyl substituent. Now we have already assigned the priorities to all the 4 substituents. So if we go from 1 to 4th, 1, 2 and 3 and hence 4, the direction will be clockwise. Hence it should be given R nomenclature. But since the fourth priority substituent is present in the horizontal line of the Fisher projection, the nomenclature, the absolute configuration will be reversed as per the rules. Hence, it will not be R, but it will be assigned as S. So, I hope the concepts have been brushed again now. So, in the further examples, we will not be covering the concepts very deeply, okay? So, you can try to solve this example as well. In this one, again, the nitrogen will be given the first priority, carboxylic acid will be given the second priority, methyl will be given third priority, and hydrogen will be given fourth priority. But since again 4th group is on the horizontal line, this nomenclature will be reversed, hence it will not be R but S. In this third example, you can see the alcoholic functionality will be given the first priority. Out of methyl and ethyl, the ethyl group will be given the second priority because the carbon atom which is linked to the chiral center is linked to another carbon atom. Whereas the methyl will be given the third priority this time. Hence, again the fourth substituent is present in the horizontal line. So, although we are moving in clockwise direction, the nomenclature, the configuration will be S configuration. So out of these two examples given here, we will solve only one of these, okay? And the other one you can solve by yourself. The answer is given already. So let us solve the second one, okay? So it has two chiral centers. If we talk about this center, let us assign priority. The first priority will go to the hydroxyl group. Second will go to this alkyl chain, which extends to the next chiral center. Third will be given to this methyl group, and fourth priority will be given to the hydrogen atom. So clearly the fourth substituent is present vertically. So whichever direction we move, the absolute configuration will be given accordingly. No reverse of absolute configuration will be made. Hence, we will move from 1 to 2 to 3, and it will go as 1, 2, 3. Okay, so it is going in anti-clockwise direction. Okay, so there must be a mistake made here, because since the fourth group is present in the vertical direction, no reversal will be made, and hence it will be assigned, it should be assigned S configuration. Okay. Again, in the second chiral center here, bromine is having the highest atomic number, so it will be given the first priority. Then the alkyl chain will be given the second priority, and the ethyl substituent will be the third priority. Hence, if we move from 1 to 2 to 3, it will be clockwise direction. But since the fourth priority substituent is present in the vertical line, the the absolute configuration must be reversed. So although we are moving in clockwise direction, we will have to reverse R to S. Okay. So this is basically coming from the concept of Fisher projection, RS nomenclature. Okay. So you can try to solve the same for this example. The answers are already given, so you can match whether you are getting it correct or not. Okay. So let us move to the other questions of today's tutorial. So This is a numerical given from the concept of specific rotation of organic solutions. The specific rotation for a given 20% solution of sugar with the angle of rotation 25 degrees and length of the tube containing the solution is 15 centimeter. We are given the concentration of the sugar solution and angle of rotation is given, as well as the length of the tube is given in centimeter. We have to measure the specific rotation. Let us revise the formula to calculate specific rotation. So, according to the laws of optical rotation, the angle of rotation is directly proportional to the length of the tube, which must be in decimeters, okay? And along with the length of the tube, angle of rotation is also proportional to the concentration of the organic solution. Hence, we can derive the formula for the specific rotation as this, which is written here. Theta is equal to S into L into C, where S is the specific rotation and L is the length of tube or path length and C is the concentration, having a unit of gram per centimeter cube. Okay. Hence, we get specific rotation as the angle of rotation divided by LC. Okay, so we will just put the values which are given in the question. So we have derived the formula S is equal to theta by LC. Hence, S will be 25 degrees divided by 1.5. 1.5 is the path length in decimeter into 0.2. So 0.2 is the concentration of the sugar solution. It is given in 20%, so we have converted it into gram per centimeter cube. Okay, so you have to remember the standard units of the values which you have to put in the formula. Otherwise, you will not end up getting the correct angle of rotation or correct specific rotation values. Hence, the value of specific rotation which we will get is 83.3 degrees. I hope this was easy for you. Then let us move to the next question. We have another question here where Fisher projections of a few organic molecules are given, and we have been asked to draw the wedge diagrams of these organic molecules. Okay, so let us solve one by one. So whenever we are converting Fisher to wedge, just imagine it as lifting the molecule lifting the molecules, holding it through the horizontal substituents. Okay, so if we lift this molecule in this way, you can imagine it as the vertical substituents will remain on the plane. whereas the horizontal substituents will move away and below. Hence, you will get a wedge diagram of the molecule in this way. Okay. Similarly, if you have to do the same for the second molecule, we will lift this molecule holding on the horizontal substituents, and the CH2OH and ethyl substituents will remain on the plane. Suppose we are placing the ethyl ethyl and CH2OH substituents as this, we will get the molecule in its wedge projection in this way. Similarly, if we do it for the second chiral center, we will get a wedge diagram of this type. Okay, so this will be the wedge projection of the given Fisher projection. Okay, so now after solving these two, it must be easier for you now to solve for the third question. And if we quickly draw it, it will be methyl here and OH here, and towards us there will be two substituents which will be hydroxy and hydrogen, and on the other side, which is away from us, the two substituents will be hydrogen and methyl. So this will be the wedge dash diagram of the given Fisher projection. I hope this is clear to you. Okay. Now we have been given two Fisher projections which we have to convert into Sawhorse diagrams. Okay, so again, when we are converting it to Sawhorse diagram, we will similarly lift the horizontal substituents upwards, and imagine the vertical substituents, which are methyl and ethyl here, will remain downward in this way. Okay, I hope you can imagine it in 3D. So the first substituent here will be methyl, and The other substituent which has gone down will be ethyl, okay? And the substituents which are towards the left will be hydrogen and hydroxy groups. I hope this is clear to you. And similarly, the second example is given, another Newman projection where we have to, sorry, not Newman, another Fisher projection is given. We have to convert it into sawhorse, okay? It's not necessarily that you have to draw in this direction only. You can draw it in this direction as well. So this will be phenyl substituent, and here you will get the tosyl protected hydroxy group, and the horizontal substituents will be methyl, methyl, hydrogen, and hydrogen. Thus, we have converted the given Fisher projections into Sawhorse projections. I hope it is clear to you. Now we are given two different Fisher projections of two molecules, and you have to figure out the molecules represented by the above two structures are whether they are identical, enantiomers, diastereomers, or epimers. So let us see how to approach to solve the question, okay? What you can do is to solve the question correctly, you can figure out the absolute configurations present in the molecule, okay? So, for example, for this first molecule, if we assign the RS nomenclature in this molecule, this particular chiral center will be 1, 2, 3, but fourth group is horizontal, so it will be S, okay? It will be S. Whereas the second group will be 1, 2, 3, again S. Let us solve the same for the second molecule, okay? 1, 2, 3. This will be S, and this will be 1, 2, 3, again S. Hence, both the molecules are having chiral centers of set S and S. Okay, you can approach this question by converting them into Newman projections as well, but that will be a time-taking procedure. So, to solve these questions quickly, you can figure out the absolute configurations of the chiral centers present in these Fisher projections, and if they're coming to be identical, you can say that the molecules given are identical, and the molecules are going to give you the same projections if you convert these Fisher projections into Sawhorse or Newman. I hope this question was clear to you. Now, this is another question given, a similar question where a set of organic compounds are given, and this time the absolute configurations are already given to you. You just have to decide these set of molecules having such absolute configuration will be enantiomers, diastereomers, identical, or epimer. So here, if we look at the absolute configurations, the first compound is having a set SR, okay? And the second compound is having a set R and S. Hence, whenever you have a situation where the sets are completely complementing each other, then you can say that these two compounds will be a pair of enantiomers. Okay? And visually also, if you look at both these two molecules, these two are mirror images of each other. If we place a mirror plane in between the two molecules. But although these two are mirror images of each other, you cannot superimpose these two on each other. Hence, you can clearly by definition announce these two as enantiomers. I hope this question is clear to you. Let us move to the next question. So we are given a Newman projection of a molecule here, and we are given 4 options. We have to identify which of these Sohor's projection will correspond to the Newman projection given.